In this omarvision tutorial, we're going to take all these procedural mesh tutorials that we've been working on, and we're going to finally like make a whole voxel terrain or a voxel chunk, which kind of looks like this. This is going to be the result of this tutorial that we're going to reach this goal. So when I have the code not running, since the mesh is procedurally generated, all I have here is like a base mesh. This is like the bottom layer, and it just helps me outline, where the mesh is going to be. Here, the terrain chunk, this is basically, it was an empty game object that I added, and then I just put my terrain chunk script on it. The terrain chunk script is what is going to make that terrain. Okay, and that's what we're going to get into, is how to write such a script as this. So my chunk is going to start from this position, which is 0, 0, 0, and it will define cubes going outward into this direction. So this is the origin of my terrain chunk 0, 0, 0. And all my cubes are also, as they are created, have origins right there in the bottom left corner going out like this. So let's take a look at here what the terrain script, terrain chunk script is asking for. It asks for a material. So I have used this cube material because it will look nice on the cubes like this for each cube. And right there on the terrain chunk script, I could drag and drop the material I want to use, just the one material for one mesh. And then there's the size of the chunk, which is going to be 80 by 80, and then the height is going to be 40. That's going to be the size. Now the Perlin loops, I'm using the Perlin noise algorithm to like make the hills for the voxel terrain, and it's always going to come out randomly, but Perlin noise is like a pseudo random noise generator because it kind of has like patterns that it makes randomly. And I said Perlin loops as a variable over here because for each Perlin noise that I apply, it just kind of makes the hills more and more, variety. So here there's 2 that I add, and the scale is like how, I'll show you how those work, okay, when we get to them. And here I could just put 2 of them. So for this element type of my Perlin loops, I made a structure. So it takes the scale of the Perlin, that's like how zoomed in or out it is on the Perlin noise algorithm, and then the height, which is how much of the height from the 0 to 40 that this particular Perlin value could affect, how many cubes it adds in the up direction. Oh, a lot of talking. All right, let's look at the script, okay? So the script, just like from the other scripts, like when I did a triangle, a quad, a cube, and then a chunk, I'm using same things from the script. And this here is just a comment where it's describing how I think of a cube, where I have these 8 vertices that make up a cube, all right? And that way, when you look over here at the enum quad, so this is the back face, the ABCD, ABDC, and this is the face facing front because the z-axis goes outward. And here with this enum quads is a way I could describe which quad or face of the cube I am trying to define. So there's just an enum quad. Then the points in the cube, right? They're always going to be the same: A, B, C, D, E, F, G, H, and C is the origin. So this static class point is a way I could talk about the points of a cube with just referencing them as a letter A, B, C, D, E, F, and G, H. And here it's their offset values from C being the origin. All right, so these 2 things just help out, make the code more readable. All right, let me shrink that down. Now the terrain parameters is what I made the structure called. It's system serializable so that you can see it in the inspector and the values are saved. It just has the Perlin scale and the terrain height like I described in the inspector window right over here. See? Perlin scale and terrain height. And the reason that you can see these little scroll bars here is because for the public float, I put a range type, and this is an instruction to the inspector to make a scroll bar where the minimum value is 0.1 and the maximum value is 5. So these 2 variables have that. And then there's some hidden in the inspector variables that they won't show in the inspector. Perlin noise offset for the X and the Z. All right, that's so that I don't keep getting the same Perlin pattern. I get it from different positions. So that's what the terrain parameters are. A nice way for me to pass that information in and for me to collect the information in the inspector window. All right, otherwise they're just variables. Now here is where all the work of generating the mesh data is done in the chunk object. All right, these are still in my region helper. I still didn't get to do any code for the class terrain chunk. But before I talk about the chunk object, now I think I'll just get down to the terrain chunk script. All right, so I have two constants, an offset of 1, and basically this is like the size of each cube is going to be a size of 1. And this percent thing is not necessary, but it was there so that I could show the cubes inside something. For example, right now it's a 1, so it looks like what you just saw. But if I put it down to a point, maybe a 0.7, right? Now each cube will be smaller. It won't take up its full size. And then if I go over here and render that at a 0.7, you'll see what that percent thing is doing, the PCT variable. It's doing this. So instead of each cube face being drawn fully, you can see that the faces are drawn just slightly smaller than their full value. See, so that's 70% of the cube faces drawn. And this just helps you to see that inside, there are no faces defined. It's only the faces on the outside that are defined. And even when you come up here to the top, you see it's only the faces on the outside that are defined. And that's why I had that percent thing there. It's really just for the tutorial, but I left it in. Okay, so that's what the percent thing's for. So let me put it back up to 1. Okay, now that you see the explanation of that. The material, so you can say what's rendered on it, have those green cubes. The chunk size is how big you want your chunk to be. So I said 80 by 40 by 80. And then the Perlin loops things, this is the randomness that I apply for the hills. I apply randomness, it's a loops, so I could apply one Perlin randomness and then another Perlin randomness on top of each other. And then the chunk object. This is the chunk object is this class right here, and it's the one that takes and makes the mesh data. Very important, but its own object right there. All right, so when the script starts, it's going to come into the start function. And let me put a little breakpoint and let's run the code so we could just run through the code and see what it does. I think that's the best way instead of me talking about it. So I'll attach this to Unity, and then I'll start the script here by pressing play in Unity, and then it hits the breakpoint because I attached it to Unity. All right. So like I said, every script start is the first thing that it hits for every script, right? So here's the start function, and we come down, and the first thing we need to do is we need to make a mesh filter and a mesh renderer on our game object because as you saw in the inspector window, which it's taking time to get to. Maybe I can't get to it. Darn it. All right. So I have to add a mesh filter component and a mesh renderer component to my empty game object, and that's what this function does. Let's step into it, and it's right here. So I'm going to have a variable mesh m. That's what I'm going to send back. Then I'm going to add a component, a mesh filter component, and the mesh filter holds the mesh data. That's its job of that component. And I'm going to add a mesh renderer component, and its job is to render the mesh data visually in the scene. Okay, so those two components are necessary. And then the mesh renderer that renders the component, it needs the information of the material that it's going to render on the mesh. So that's here, mesh render, I set the material. Okay, so now I got my mesh renderer and my mesh filter. Now, for my mesh filter, I need to make sure I have declared or allocated a mesh object, right? So I noticed that there was a difference if I'm in the editor. If I'm in the Unity editor, I have to use shared mesh. And if I'm using a compiled Unity exe, I just use mesh. So here it checks if I'm in the editor. And of course, I'm in the editor because I'm running all this code in debug mode. So I use the shared mesh. And at first, that's null. See, so it's null. So I check to see if it's null before I allocate a new mesh. Okay, and then I set m equal to that. And now m is not null anymore. Now there's an allocated mesh. There's no data for the mesh, but there is an allocated mesh. And we come down here. Now, the index format by default is uint16. So that means there's a limit of how many vertices you can have in your mesh of 65535 because it's only 16-bit. But what I do here is I change it to 32-bit so that my index, I could have more vertices in the mesh of about 4 billion instead of just 65535. So I changed the format there so I can make bigger meshes. And then the name of the mesh, by default, I just allocated a mesh. There's no name. So here I just give it a name so I can see the name in the inspector window. And then I return the mesh. So get mesh finishes job of giving me a mesh. So it returns the mesh right here. Now that I have a mesh, I want to define what the data for the mesh is going to be. So I'm going to use my chunk object class here in my helpers. Okay. So the first thing I do is I have to allocate a chunk object, right? So my chunk object variable is going to equal a new chunk object instantiated class, and I pass it the size x, y, and z that the user specified in the inspector window, and I pass it the Perlin loops that the user specified in the inspector window. So chunk z is a vector 3, right? And vector 3s are floats. So I just typecast each float as an int because chunk object, the constructor wants integers. So now let's step into this new chunk object function. See, so now it comes into the chunk object class of my helpers. And the first thing it has to do is run through and give the default values for all my variables. I always like giving everything default values there. And then I finally come to the constructor that I'm stepping into. And here you see it wants ints. So I got 80, 40, 80. And my terrain parameters is an array of 2 of them, where this first one is per length scale of 5, 0.5, and 0.2, and the offsets are not defined yet. And then the second in the array is a 4 and a 6, and the offsets are not defined yet. All right, so let's come in and start the constructor. First thing we're going to have to do is figure out how big do our vertices, triangles, and UV arrays, how big do they have to be to hold data for a chunk size 80, 40, and 80. So that would be the 3 dimensions multiplied by each other. That's how many cubes they're going to be. And then how many vertices each cube has, which is 36. So for this, our array size is going to be 920. It's going to be 9,216,000. There's a lot of vertices we're going to have in this. Okay, so our vertice array is null. We're going to allocate, allocate, and allocate. And hopefully there was enough memory on your computer to allocate each of the arrays of that size. Otherwise, there would be a runtime error, and we'd have to do something about that. We'd have to like shrink the size of the chunk on the computer you're working on. But my computer has enough to hold 3 arrays of that size. Now these values here that were passed in, I think it's valuable to know them in the rest of the class, so I'm going to store them in a class variable, size x, y, and z. And now let's take a look at the terrain parameters that were passed in, that array of 2, and we're going to have to copy it internally into the class to its terrain parameters variable. First thing we have to do is allocate the terrain parameters variable to the right size. So that is a size of 2, because there were 2 in the one that was passed in. And now for each of those items in the terrain parameters, we're going to have to define the values. So we copy the values from the one that got passed in to ours. So we're basically just making a copy of the terrain parameters that were passed in locally into our class chunk object. Okay, so we allocated the arrays, we copied some values, and now we have this other object in the chunk object called cube objects, and it's a 3 by 3 array. So it's a 3 by 3 array on x, y, and z, and it's just a Boolean value to say if that cube is on or off in that position in the chunk. So first we have to allocate that array because as you can see here, it is null. We couldn't allocate it in here because we didn't know how big the chunk was going to be. But now we know, so now we can allocate a new array of size 80, 40, 80. 1 bool for each cube in the chunk. Bam. And now let's init the cubes, okay? So let's see what that does. Let's step into that, and here's init cubes. So first thing, remember from the terrain parameters, the Perlin offsets were 0. So the Perlin offsets, they're just going to create randomness. The Perlin has a pattern of randomness. It's a pattern of randomness, but if I keep feeding in the same values, I start from the same values, it's going to give back the same pattern, the same random pattern. So here what I'm trying to do is I'm trying to feed in a random offset for the x and a random offset for the z so that the random pattern is not the same random pattern, but it moves a little bit. So for each of my terrain parameters now, I'm going to define the offsets for my 2 terrain parameters. So now if I look at my TP array, I have index 1. You see the x offset starts at 0.37, blah, 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 and the z offset starts at 0.71. Okay, so that's the first Perlin noise values that I'm going to use. And then on the second, it's 0.01 and 0.75. So that just makes the terrain look a little bit more different. Helps with the randomness of the terrain. So I just went through my terrain parameters array of 2 and did that first. Now I'm going to go through, and for every cube position in my chunk, for the z, y, and x, for every cube position in my chunk, I have to go through all 3 dimensions. I'm going to do this inner loop here. So let's get down to the inner loop and see what it actually does. All right, so first I have a height, I say is 0. So for every column, every y column in my terrain, I have to figure out how high is this cube position. Ooh, I think I have a boo-boo. And I'm going to see, based on the height, if the particular cube at this ZYX is on or off. This may be getting confusing. Just try to take it slow. So now I'm going to apply to the height, like how high is this column going to be. I'm just going to apply the Perlin noise algorithm 2 times because my terrain parameter's length is 2, so I'll apply it 2 times. All right, so on the first time, let's see how high this column is going to be of cubes, where it determines if it's on or off. Let's see. So we're going to use, for the Perlin algorithm, we're going to feed in an x value of 0.37. These x values and z values, they have to be between 0 and 1. Okay, so that's why I'm dividing. I have this divided by this plus the offset, and that could make it past 1, but oof. So I have an x value and I have a z value, And now I'm going to call the Perlin noise algorithm, which will give me a random float based on the x and z value. But these random floats are in a pattern, and they smoothly change from one to the other. But at this x value, z value, what will it be? It's 0.45. The other thing I do is I multiply by the Perlin scale. That just would kind of be like if you were to see the noise of the Perlin noise if you zoom out. It looks more noisy. If you zoom in, it looks more smooth changes in value. All right, so now what's the height going to be? So far my height is 0. So on this loop of terrain parameters, I'm going to add to my height of 0, and then my height will be 3.6. Okay? Now in my next iteration, I go through. It's now 3.6. I'm going to add, and now my height is 13.8. So from 0 to 40 in the y column, everything below 13.8 is on, and everything above 13.8 is off for the cubes in this y column. So now that's what I do over here. Let's just jump over here by run to cursor. Where are you, run to cursor? Run to cursor, and we'll run right to here so we finish going through that loop. And we'll see 13.8. And for this particular cube at x, y, and z, this one's going to be on, right? Because this is a Boolean operation when I put the parentheses, and it says it's true. So this cube at 0, 0, 0 will be on. So we're going to loop through that to find out every single cube, whether it's on or off in init cubes. And we sooner or later will come to the end of this looping for all the cubes. There's like almost a million. So let me run to cursor, and now we finished editing all the cubes. So this giant cube array of 80 by 40 by 80 cubes, each one of them has been decided in the cube objects if it's true or false. True is the cube will be drawn. False is the cube will not be drawn. It is off. So we could come out of the init cubes, which job was to say which cubes are on and which cubes are off. And we come out of that, and we're back here in our terrain chunk class, okay? And the next command here, after we allocated and define which cubes are on or off, that's what the constructor did, is to define the mesh data. So, and that is still part of the chunk object, which is taking a lot of the work of defining the data. So now after we said which cube is on or off in the constructor, we're going to define the mesh data for each cube that is on. So now we step into here, and with all this looping and everything, I put the bool to say whether the cube is going to show a quad or not as outside the loops. So when I draw a cube, what I'm trying to decide is which quads of the cube are going to be rendered. Like you saw when I just did the demonstration that the inside of the terrain, nothing is drawn. I'm not going to render faces for things that are inside the terrain that the camera can't see. So I have to decide which cube sides of the cube are going to be drawn. And I'm calling a cube side, cube face, or cube quad. I'm going to use the word quad, all right, because 6 quads will make up a cube. So here, when we go through this z, y, and x, we're at a cube. Okay, so for this particular cube, we're going to loop through each of the sides to see if we have to render it or not. So let's get into the inside of that loop for an example of one cube and what it does. So an enum quad had 6 values, right? Here's the enum quad. And there were 6 values to describe the 6 sides. So here, oh, where am I? Show next statement. So here, I'm going to loop through each of the enum values. And this is the syntax for how to loop through each of the values of an enum. Okay? So the first quad value, the first enum value, is the back. And we have to figure out the offset for this cube that is the back. So we're going to do this little algorithm, this little math here. It's the x plus the y times the size of x plus the z times the size of z and the size of y. And then each cube has 36 vertices, and that will be our offset into our vertices array. So this particular cube is offset at 0 because we're at x, y, z 0, okay? And then the position offset for this particular cube in the chunk is 0, 0, 0, because we're at 0, 0, 0. So with the vertice offset and the position offset, we can now define sides. First we have to check, is this cube even on? And it's not off. So we're in the cube on section of the if statement here. And now for which quad it is, we're going to define whether that side is going to show or not. So the quad is the back. So boop, we're going to pop right here into the back. And we're going to check. So if we're at the back, we're going to do the back quad. We have to see if there's a cube that's on behind me. Because if there's a cube that is on behind this cube, then I don't have to render the face. Because 2 cubes are right next to each other. You're not going to see those faces. All right? So the cube behind me would be x, y, z minus 1. That's the cube behind me. So let's just see, let me highlight this here and see if there is a cube behind me. And this is going to say, what's that, quick watch? This is going to say that it's unable to evaluate the expression because at x, 0, 0, and z, 0, there is no minus. So that's why I have this here. If z is greater than 0, then I will check the cube object's value, if it's on or off. And this little thing here means not. So it reverses whatever the cube object value is. But here, if z is greater than 0, z is not greater than 0. So this question mark means that if this is true, it does this. And if this is false, it does this, what's on this side of the colon. See the colon symbol here? So z is not greater than 0, so I am going to show this face true. Boom. So we go ahead and we're going to do that for each of the faces, deciding whether we're going to show or not. So I think if we get to here, the back was off, but here if we get to the front one, we should be able to see something. So let me run it till we get to the front one. Run to cursor. All right, so now here we're going to do the face in front of my cube. And since z is 0, z is still 0, there is a face in front of my cube. So now I'll show you how this question mark thing works when I come into this part. All right, so here I have to see if z is less than the size of z, minus 1, because I'm going to add 1. So this equals, let's see what that equals, quick watch. That equals true. Good, so that means we're going to run this part of this question mark semicolon thing. So let's see what cube objects at x, y, z plus 1 equals, if it's true or false, is this cube on or off that's in front of me? And it is on. So the cube in front of me is on, and I'm on. So that means the wall does not have to be drawn. So even though this said true, I'm going to flip the value of true with this not, this exclamation point flips the value so that I do not draw this wall. See, now I'm selecting it with the exclamation point and it'll be false with the exclamation point. So for the front wall, I will not be showing the front wall. See, so show equals false. Then when it gets down to here, I'm going to define the quad. I'm going to define the vertices for the quad front with the vertex offset and the position offset, and I'm going to say whether I'm going to show it or not. So let's step in, and here's the define quad. So I'm going to go by which quad you said, the front, so it goes into the front, and if I'm going to show it, then I'll define the vertices, you know, the way it should be at that position offset and that vert offset, but it's not going to show, so I'll just set all the vertices to nothing. 0, they're not going to render anything. 0 doesn't, it's not going to have any representation in the screen. All right, so now the vertices are all 0 for this quad of the front of this cube. And the triangles, they point to the vertices to say how to draw the triangles, how to connect the dots. And the UVs, they say how to take the material, which is a flat, you know, two-dimensional image, and from what corners of the material do I draw it on what vertice. Those are always the same. And that defines a quad. So now I'd come out, and it would just loop, and it would do this for every quad of every cube. And the loop is big, that's why it takes a while. So let's just get here to the end of that function, run to the cursor. It's going to take a while. This is where it's looping through everything, and then it comes here. Then we come back out. We defined all the mesh data of the chunk now. So now we know which cube is on or off, and for each cube that's on, we know what quads are going to have a face to render. So we have all the data for our mesh, so now we have to set the mesh. So this mesh object that we got here that doesn't have any data yet, now we're going to set the mesh data with set mesh. So we go in. So the first thing we do to the mesh is make sure that there is no data. So we clear the data out. Then we set, this is the vertices, triangles, and UV from our chunk object here. Let me try to show where we are. Because set mesh here, this is in the chunk object here, the chunk object class. All right, so we're going to set the mesh vertices, triangles, and UV. And then once you set all that data for the mesh, you know, Unity has to do some calculations to know how the light's going to shine on that side, on that triangles. So we recalculate the normals. Unity's going to have to know how big the mesh is, so we recalculate the bounds. And Unity may have to know some things for if there's a shader graph or something that's built on the mesh, so we recalculate tangents. Ooh, that one took a while. All right, so the mesh is set. Let us go back now. We have a mesh with data. That should be renderable. Now, if we want to actually have collision detection, we have to set a collider. So this function, set collider, is going to show us how we do that. To this mesh that we procedurally generated, let us dynamically add a collider. So let me step into this. And it's kind of simple, because first we have to add a collider component. And the type of collider component we're going to add is a mesh collider, so it matches exactly the contours of our terrain. And then we just have to tell the mesh collider what is the mesh, right? So I'll just tell the mesh collider, this is the mesh that we're testing for collisions with. Bam, and then there's a collider. And that's it. We finished going through the start function. And now if I let it go, let's let her rip, we're going to see what the terrain looks like. But the only thing, let's test to see if the collider works. So to do that, I'm going to have to add something to the code, to the scene here. Let's add some balls to drop and fall on the terrain. So let me just create an empty, because I'm going to create a couple of balls here. I'll say balls, and I'll pick it up in the air, and I can't even really tell where I am. Okay, I'll pick it up in the air, I'll put it like here. Oh, let me see where I am over the terrain. Oh, okay, that's below. All right, so I'm kind of here, up in the air. I have to have time for the terrain to get rendered before the balls fall on it, so I'm going to pick the balls up a little higher. Now let's add some spheres. All right, and there's a sphere. It has a collider. Just have to add a rigid body so it could drop. And they're kind of small. The terrain's really big. Let me just make the balls a little bit bigger so we could see them, okay? And I guess they could just stay white. So that's one. Let me duplicate. Just make a couple of them. All right. Just to test. And let me make another one. All right, so we got 3 balls that should fall and collide on the terrain. Now I'm going to run it again. So remember, the terrain chunk is not generated yet. I have to generate it before these balls could fall on it. Here we go. Let's see what happens. It's going to go to the game view. So everything's getting generated. Boom. And the balls are coming down. And you see, since there's a collider on it, the balls hit the collider and move. So that's the end of this tutorial. And I think in the next one, to make it like Minecraft, we're going to make a player walk through the terrain and be able to maybe add and remove cubes like Minecraft. All right, bye-bye. You made it to the end of the video. I'm so proud of you. This is my website. The main thing I want to show you is that for any of these videos that you've seen on YouTube, I have the tutorial section, which has the blue links for the projects, and the orange links are the files. Also, you could go over here and play some of the games we made in the game camp.